Hi, I'm Wannes, and I would like to present to you our study on viability qPCR, published in Applied and Environmental Microbiology. Viability qPCR is a technique that allows us to detect the DNA of living cells specifically through discounting that of dead cells. This can be achieved by using a dye such as propidium monoazide, which cannot enter the membrane of living cells, but it is able to enter membrane-compromised cells, or in other words, dead cells, that do not have this protection. Once inside, it likes to intercalate with the DNA, and if it's photolyzed, it can irreversibly bind to the DNA. While it can have many functions, once bound to the DNA, its main purpose is to block polymerase chain reaction and thus reduce the signal in qPCR. So, the dead cells that had PMA enter them and then bind to their DNA will be discounted in our qPCR, resulting in the only detections remaining being from live cells. While in theory this is quite useful, we noticed that there were some limitations that weren't described that well in literature. Concretely, we saw that the signal reduction was present. It wasn't that great. Were the cells really alive, or maybe were we getting some kind of live signal? When completely heat-killing our cells, we only saw a 2-log reduction, which was strange because there was no subsequent growth on any of the growth media. Ideally though, our viability qPCR should have an accurate distinction between live and dead cells. So, to theoretically solve this, we looked at 3 possible options. The first being there might be some limitations on PMA entry. The second being that the PMA binding may be limited. And thirdly, even though the PMA should stop the polymerase reaction, possibly the amount of PMA bound was not enough, resulting in no significant reduction of the signal. After optimizing the first 2 causes, we saw that there was only a minor improvement in our signal reduction and saw that there was a lot more room in reducing the signal in the third. Using Aggregatibacter actinomycetum comitans as a case study, we designed 32 primer sets and tested these both on live and killed samples in parallel to see what the effect is on the CQs. All primers naturally had similar properties to that of the originals to make sure that this does not confound the results. So, what did we see in this case study? Well, we saw that the CQs, or quantification cycles, drastically increased with amplicon length, mostly in the dead cells, and a lower CQ means a lower amount of detections. This was independent of qPCR chemistry, as the dye qPCR gave this exact same result as the probe qPCR. This together indicates that increasing amplicon length is quite important to reduce the signal of your dead cells over your live cells. Fortunately though, there is a very important trade-off in qPCR. Usually qPCR uses shorter amplicons because these are more efficient and give better results. Longer amplicons usually have a lower efficiency, meaning that they're less specific in their detections, but also show higher standard deviations. But as we just saw, longer amplicons give a better difference in CQ values. This thus poses us in front of an important dilemma. Is there a trade-off that we can take between delta CQ and its efficiency, and how can we optimize this? For this, we propose 2 methods. The first being that you can look at delta CQ and you can choose yourself, or you can take the derivative of delta CQ over the amplicon length, which gives us the behavior of delta CQ. From this, we can look, for example, at the inflection point or at 5% of the maximum. The live detections of both of these are still quite good, but more importantly, the signal reduction in the dead is naturally a lot higher. The nice thing about this setup is that you can already do this with just 6 amplicons, which we validated in several other species. The second method is more quantitative, but also a little bit more time consuming. In this receiver operator characteristic-like curve, we plot the delta CQ versus the inverse of the efficiency. This can give us the max perpendicular distance, which is the best trade-off between both the efficiency and the delta CQ. Or you can arbitrarily choose your maximum reduction in efficiency to see which delta CQ you can still get at which amplicon length. To get this, you unfortunately need a bit more amplicons and a dilution series of each. So from both of these methods, we can then choose a new amplicon for Aggregatibacter actinomycetum comitans. From method 1, we see that amplicons around 224 to 400 base pairs is pretty good, and from method 2, we see that 242 is ideal. So we chose the amplicon that we had already designed between these two, being 237. Now, what does this all mean in practice? Well, if we look at our original amplicon, in which we only saw a 2-log reduction, when comparing our longer amplicon to this one, being the 237 base pairs, we saw that there was no significant reduction in the live detections, but the kill samples had drastically lower detections. The new amplicon is a drastic improvement over original amplicon, being almost 3.5 log lower. So, if you ever design a viability qPCR assay, please do consider increasing your amplicon size. Thanks for listening.